Hello everyone, I am Maria Clemencia Ortiz and I will present my work on the role of neural oscillations in early speech perception and language acquisition, which has been directed by Judy Gervan. So at the beginning of life, can you hear me properly? Yeah. At the beginning of life, newborns face a challenging task that is learning language from a continuous signal that is a speech. So this even though parents speak maybe in a infant-directed speech is still a continuous signal. So they have to learn from this continuous signal. They have to segment words and extract the grammar of the language that they hear in their environment. Oh no, this is horrible. This is not the way it's supposed to show. Oh, okay. So. No, but also, I don't know. I have to get very close. But okay, so the figures got damaged from, I made it in Mac. Anyways, so one neural mechanism that has acquired a lot of attention in the last years to study how infants acquire language is called to study speech perception, it's envelope tracking. So this has been mainly studied in adults, and it consists on the way that the neural signal follows the slow changes that the speech signal has over time. So this has been shown in adults, but it had not been investigated in children. So in my project, I investigated this as speech envelope tracking has been associated to comprehension. It has been shown that when listeners understand what they are hearing, then the signal is followed more closely than when the signal is not understood. This one shows properly, yeah. Another neural mechanism that has also been studied for speech perception is that of neural oscillations. So neural oscillations correspond to the firing of neuronal assemblies, and to study neural oscillations, then the neural activity is decomposed in frequency bands, which have been grouped according to their functional characteristics. So they have been decomposed in bands that are called delta, theta, beta, alpha, beta, and gamma, but the ones that have been associated to speech processing are mainly delta, so the slowest oscillations here in red. They have been associated to the processing of intonational phrases. Also, theta oscillations have been associated to the processing of syllabic units, and gamma oscillations, so theta corresponds to the activity between 4 and 8 hertz, which also corresponds to the syllabic rate of most languages. And then the gamma oscillations have been found to aid in the processing of phonemic information. Additionally, so neural oscillations have been studied in animals and in adults, but not so much in children and also not so much in newborns. Additionally, it has also been shown that neural oscillations are organized hierarchically. So the slower oscillations, for example, delta, they slave the faster oscillations. So the amplitude of delta, it has been shown that the amplitude of delta oscillations modulates, the phase of, the amplitude of delta oscillations slaves the phase of theta oscillations. So also, I have investigated this at BERT because the developmental origins of neural oscillations had not been investigated in humans. So we didn't know whether at birth these oscillations were already in place and whether this hierarchical organization was already in place at birth, or whether it required a long experience with language. So as we know, language acquisition starts before birth, as hearing is operational already in the last trimester of pregnancy, so between the 24 and the 28 weeks of gestation. However, the speech signal that reaches the fetus is not the same as speech as we hear it outside the uterus. as the maternal tissues act as low-pass filter. So the maternal tissues and also the amniotic fluid filter the speech signal that reaches the fetus. So what they hear is a muffled version of the speech signal. However, this low-pass filter version preserves the prosody of the language. So they do receive the prosody of the language that their mother speak, and this prosody, it's enough for them to gain a lot of knowledge from their mother's language. So here, for example, we see a spectral representation on the left of what the speech signal looks like in the uterus. So it mostly contains low frequency information, and then after birth, then they start to experience the full band information where the higher frequencies are also present. So therefore, because the phonemes are contained, the phonemic information is present in the higher frequency information, at birth, newborns are not very familiar with phonemic units, but mostly with the low frequency components of the language. So because at birth they have only had experience with the low frequency components of the speech signal, we hypothesized that at birth we will only be finding low frequency neural oscillations. And then later, as they acquire experience with the full band speech signal, then the higher frequency oscillations, therefore gamma, will appear later, not at birth, but later in development. So to investigate this, we recruited newborns, so 47 newborns born to French-speaking mothers, monolingual mothers. So they were only familiar with French at birth, and we followed some of them at 6 months. And then we had to recruit more at 6 months because not many came back. And we presented them with sentences in 3 languages. So in French, which is their native language, in Spanish, which is an unfamiliar language to them, but that is rhythmically similar to French, and also in English, which is both unfamiliar, but also rhythmically different. So the reason to choose these 3 languages is because it is known that at birth, infants can discriminate languages on the basis of rhythm. And this is not exclusive of humans, also monkeys can do it. So they will be able to discriminate 2 languages that belong to different rhythmic classes, even if they don't know the languages. So following this, they will be able to discriminate French from English and Spanish from English, but they will not be able to discriminate French from Spanish because they are rhythmically similar. We also recorded a resting state activity before any speech was presented, and some also resting state at the end, but I will not be presenting the results for that because we don't have enough time. I don't know if I can play.
The bears lived all together in a beautiful house.
So that's an example.
Les ours habitaient tous ensemble dans une maison.
Los osos vivían juntos en una casa.
So this was in mild infant-directed speech. So first we investigated envelope tracking. So I know you didn't see the figure at the beginning because it was distorted, but envelope tracking consists on how well the neural activity follows or tracks the shape of the envelope of the speech signal. So the envelope of the speech signal is the slow information that the speech signal conveys. So here we have in black the envelope of the speech signal for each sentence for English, French, and Spanish, and for the 2 groups for newborns and 6 months. And we have in red their neural activity. Although in some of them is not very clear, but for example, here in French at 6 months, I don't know, does this move? No, doesn't move the cursor. But you could see how well they follow. I mean, this is considering that this is babies, and also on the left, you have it for newborns for French, that even though they are not identical, this is pretty good. It's similar to what has been found in adults. So how well it mirrors, it follows the activity. So this is what is known as a speech envelope tracking. Now looking, this was only for one infant. Now looking at the group results, what we have here, so there are two ways of measuring envelope tracking. So it's how well it follows the amplitude of the signal, how well it follows the phase of the signal. So these are just two methodologies. So we measure both. And at birth, we found that newborns were able to track the speech signal very well for the three languages. So what we have here in dots, sorry, I didn't mention that we recorded EEG. So we recorded EEG simultaneously as newborns were listening passively to this stimuli. So what we have here in colors is in which channels we found that tracking was significant for each language. So blue for French, green for Spanish, and orange for English. And as you can see, most of the electrodes have all the colors. So what this means is that we found that at birth, newborns were able to track the speech envelope for the three languages, both in amplitude and in phase. So this suggests that envelope tracking is a universal auditory ability that is not influenced by prenatal experience, and it's not influenced by prenatal experience. So they were able to do it for the three languages. Then we followed up this at 6 months, and we found a difference. So at 6 months, amplitude was influenced by language familiarity. So only was present for English. So as you can see, all the dots are orange. So we found that they were still able to track amplitude for English, that was the unknown language, rhythmically different. Very little for Spanish, which is also an unknown language, but rhythmically similar to the native language, and not at all for French. However, for phase, they were still able to do it. So this suggests that following tracking the phase and the amplitude of the speech signal represents different mechanisms, so it encodes probably different information that is used for different tasks. And the amplitude tracking, it's influenced by familiarity. So we hypothesize here, so I'm gonna throw the conclusions right away because at the end there's not gonna be time. So what we hypothesize here is that the envelope tracking of the native language experiences a change from auditory to linguistic. So at birth, tracking is auditory, so they are able to do it for the three languages, regardless of being familiar with it or not. And this we will test in the future with other stimuli, with music, with animal calls, to see how universal it is, to see if it's present also for other types of stimuli. However, at 6 months, this turns into a linguistic ability. So it is not present for the native language, because for the native language, they already have much more knowledge. So they are busy processing other information. So there are other features that are being processed at a higher level. So they already know the phonemic information. So their amplitude tracking is found in the lower frequency bands. So they are busy processing probably phonemic information, and then there is the higher informations that are involved at this point. So it's absent for the native language for this reason. However, for English, because they are not familiar with this language, they continue to process it acoustically. And that's why we find it for English and very little for Spanish. So this was envelope tracking. Now we move into neural oscillations, which I'm going to do it quickly. So here we have the results for the 5 conditions. So as you can see, for the naked eye, they look quite similar. However, if this is rest on the far left, then for the 3 languages, and you could see just quickly that there is, so more red means higher activation, so warmer colors, red means higher activation, and colder colors like blue means lower activation. So as you can see here there is a big blob of red for French and Spanish and English, so for the 3 languages, that is not present at rest. So right away you could tell that there is a difference in activation for speech versus rest. So there is more activation during speech processing than at rest. This is for newborns. Of course, we ran stats on this, so I'm gonna go, and then I'll go back. So we're ready to have a stronger effect. We average the 3 languages together to have a speech response. So here we have the oscillations for speech, and on the left, the oscillations at rest. And we found that in the lower frequency bands, so delta, that goes from 1 to 3 hertz, and theta, so delta is the bottom figure, and then theta, the one in the middle, that goes from 4 to 8 hertz. What's in the rectangles shows what was significant, the significant difference. So there is a stronger activation during speech processing, both in the delta band and in the theta band during speech compared to rest. So this tells us that neural oscillations at birth are already engaged in in the processing of speech, of language. We are not looking here at if the native or the unfamiliar languages. Then we looked at language differences, because as I told you before, at birth, newborns can discriminate rhythmically different languages. So we wanted to see if this will be reflected in how neural oscillations are activated. So once again, we found differences in the low frequency bands, in delta and in theta. So at the bottom, we have 2 channels that show differences in delta. So again, the black rectangles show zones of higher activation, and the pink rectangles the same but with lower activation. So we can see here the activation was stronger both for French and Spanish compared to English. So this suggests that is neural oscillations in the low frequency bands that support this ability that newborns have to discriminate rhythmically different languages. This has been shown before, but behaviorally, with behavioral studies, measuring the suction of newborns with a pacifier. So this is the first time that this is shown at the neural level. So where how languages are treated differently at the neural level. And once again, we found differences between the rhythmically different languages, but French and Spanish were treated similarly because they are rhythmically similar. So this goes hand in hand with the behavioral studies. And lastly, we also investigated the hierarchical organization of neural oscillations to see if the lower neural oscillations, the lower frequency ones, were already modulating the behavior of the higher frequency ones, and we found that yes. So this figure what shows again where there is darker colors is where the frequency of the lower ones is modulating the amplitude of the higher ones, and we see like on the left for initial rest, we see that delta oscillations, so 1 to 3 hertz, are modulating the amplitude of theta and beta, but that this hierarchy is present at rest and is not modulated, doesn't change during speech processing. So it is present at birth, but it's not yet activated, it's not yet playing a role during speech processing. It will probably come later with experience, and we're investigating this as we are finishing right now, collecting the data for 6 months. So we have some data for 6 months, but for this we need more. And 24 months as well, to see how this changes in the first 2 years of life. And I'm just gonna skip through this, and thank you.